since a natural substitute of ui is ei, as we found in our earlier discussion, ui is unobservable, and therefore, in context of estimation, we discussed the idea of residual ei. Ei is yi minus yi hat, observed minus estimated, observed minus estimated, okay? And therefore, ei is observable. We can observe ei, we can realize the value of ei. So since in place of ui, we are using ei, so why not, when we are trying to find out an unbiased estimator of sigma u square, why not let's start with the variance of ei. So once again, I am repeating, ui is not observable, and for that matter, we replace ui by its some sort of estimator, which we call ei, the residual. Residual is some sort of estimator of ui. So since we use ei in place of ui, therefore, while we are trying to calculate variance of ui, naturally, the idea which comes in our mind is variance of ei, an unbiased estimator of variance of ui. Okay, so let's start with variance of ei then. And in our due course, we need to check whether variance of ei is unbiased estimator of variance of ui, or we need to modify it, or it will be something else. So that I need to check, that we need to check. So we are defining variance of ei. You can use the standard formula because ei is not random at all. ui is random. However, ei is yi minus yi hat. So you are getting observed by difference between the observed and estimated. Estimated is a fixed one. Okay. So it's not the random variable. So you can use the standard formula to calculate the variance of ei, 1 by n summation ei minus e bar whole square. Now, by the first normal equation, we find that summation ei is equal to 0, and hence e bar is equal to 0. So, as by first normal equation, we get this. Therefore, e bar, this implies e bar is equal to 0. So, the variance formula reduces to 1 by n summation ei square. Now, what is summation ei square? It is the residual sum of squares. Residual sum of squares. So, variance of ei is RSS by n. Residual sum of squares by n. Therefore, the small sample counterpart of variance of ui is RSS by n. Small sample counterpart of variance of ui is RSS by n. Hence, to estimate an unbiased estimator of sigma u square, let's start, or let's first check what is the value of expectation of RSS. 1 by n is a constant. So if I can show that expectation of RSS is equal to n sigma u square, in that case, really the variance of ei is an unbiased estimator of variance of ui. So we are starting from that point. We are starting from the point of variance of ei. Any question? Anything? Everything is fine?
Ma'am, একটা question আছে.
Yes.
Ma'am, আমরা আগের সেমিস্টারে যেটা করেছিলাম যে যদি স্যাম্পল মিন আননোন থাকে তাহলে ওটা ক্যালকুলেট করতে গিয়ে আমরা 1 ডিগ্রি অফ ফ্রিডম লুজ করব, তাহলে এখানে যে ই বার ইকুয়াল টু 0 ওইটা ক্যালকুলেট করতে গিয়েও আমরা 1 ডিগ্রি অফ ফ্রিডম লুজ করব না?
স্যাম্পল ভেরিয়েন্স যখন তুমি ক্যালকুলেট করছিলে, ইবারটা তো ঠিক দেখো স্যাম্পল রিলেটেড ম্যাটার ওইভাবে তো আসছে না। তোমার যেটা ব্যাপার ছিল, একটা নর্মাল ডিস্ট্রিবিউশনে তোমার দুটো প্যারামিটার ছিল, মিউ আর সিগমা স্কয়ার। তো তুমি সিগমা স্কোয়ার ডিরাইভ করবার সময় কোয়েশ্চেনটা হচ্ছে যে তুমি মিউ ইউজ করবে না এক্স বার ইউজ করবে। তুমি যদি মিউ ইউজ করো, you are not losing any degree of freedom. However, if you use x bar, in that case actually you need to estimate x bar and you are replacing it. Here the context is a bit different. It's not that you have two alternatives. You have either a population element that you can use or the sample element that you can use. Okay, so ei is, and on the basis of that you can calculate e bar. So no question of losing degrees of freedom in this context.
Okay, ma'am. Okay, ma'am. Thank you.
So as I mentioned, I have to check expectation of RSS. Okay, so RSS I'll define, redefine, and then I'll take expectation. Please read all small notation as capital notation. Actually, when I developed this entire thing, I used the small notation following the similar definition of that of capital. However, for many references, small indicates the deviation. So for the online classes, I'm telling you to maintain a single notation. Otherwise, you may face some kind of confusion. Okay. So while you are reading this thing or doing this thing, please read all small notation as the capital notation. I didn't use the small notation to indicate the deviation form. Okay. So I'm just adding. Okay, so please keep this point in your mind because it's a big derivation, and you are finding everywhere I use the small notation. Small notation, I'm repeating, has not been used to indicate the deviation form. I have used the small notation which is equivalent to that of the capital YI and capital XI as you are learning. So residual sum of square, that is summation I is equal to 1 to n yi minus yi hat whole square. As you know, it is the difference between the observed and the estimated. Then what I am doing, I am considering summation I is equal to 1 to n yi minus y bar minus yi hat is there, and I have to write one plus y bar. So plus I am writing. However, instead of writing y bar, I have written y hat bar. Yi hat minus y hat bar. Now look at the right hand side. Yi hat is equal to alpha hat plus beta hat xi. So if you consider summation yi hat, that will be n alpha hat plus beta hat summation xi. In the next step, if we divide both sides by n, it is summation yi hat by n is equal to n alpha hat by n, which is alpha hat, plus beta hat summation xi by n. So this is y hat bar, and this is again equal to alpha hat plus beta hat x bar. Okay. Y bar is also alpha hat plus beta hat x bar. So y hat bar is equal to y bar. Okay. So in place of y bar, safely we can use y hat bar. So y bar and y hat bar are similar, and for that matter, I am using y hat bar here. Next, I hope you are understanding. I'm replacing both yi minus y bar and yi hat minus y hat bar in terms of the regression. Now yi is equal to alpha plus beta xi plus ui, and y bar is equal to alpha plus beta x bar. So there will be a cancellation between the alpha. We will get beta into xi minus x bar plus uy minus u bar. If anyone has any confusion, I can show it. Please check whether you are understanding yi minus y bar is equal to beta into xi minus x bar plus uy minus u bar. Is there any difficulty, anyone? Shivani, is it understandable?
Yes, miss.
Shukanya?
Yes, ma'am.
ম্যাম
Yeah.
ম্যাম বলছি ওইখানে ওয়াই বারের জায়গায় ওয়াই হ্যাট বার কেন নিলেন একবার বলবেন? মানে দুটোই তো সেম অ্যাকচুয়ালি, আপনি এখানে ডিরাইভ করে দেখালেন, তো ওখানে ওয়াই হ্যাট বারটাই কেন নিলেন?
Notational matters এর জন্য। This was yi hat, so to maintain the notational matter, actually we are taking difference of the mean from these estimated value to present the thing in that way. I'm considering y hat bar and telling you there is no inconsistency if I take y hat bar, because this y hat bar is equivalent to y bar.
ওকে ম্যাম,
This is the notational matter.
ওকে।
So everybody is understanding yi minus y bar is equal to beta xi minus x bar plus uy minus u bar. If you have any confusion, you should write down the value of yi, you should write down the value of y bar, and please check whether you are getting these things or not. On the, if I take the difference of y hat bar from yi hat, in yi hat term there is no ui. When I am considering the estimated value, the difference between the observed and estimated is observed consists of random error term, while the estimated does not have the random error term in it. So when I am considering yi hat minus y hat bar, in that case, the uy minus u bar component will be not there. Okay, and please remember, when I am taking yi minus y bar, I am getting beta, and when I am considering the hat part, I am getting the estimated value. The things are equivalent, however, one is presented in terms of unknown parameter, whereas the other is presented in terms of the estimated values of the parameters. So the second part is beta hat into xi minus x bar. So if you understand this equation, we can write the thing as ui minus u bar, and xi minus x bar I can take common, so that beta hat minus beta into xi minus x bar. So the final position before taking the whole square is a minus b whole square. Ui minus u bar minus beta hat minus beta xi minus x bar whole square. After that, I am considering the whole square. So a square plus b square minus 2ab. Ui minus u bar whole square plus beta hat minus beta whole square xi minus x bar whole square minus 2 beta hat minus beta xi minus x bar into ui minus u bar. Next step, I operate summation on each of the three terms. So the first term is summation ui minus u bar whole square. Second term, beta hat minus beta whole square into summation xi minus x bar whole square minus 2 beta hat minus beta summation ui minus u bar into xi minus x bar. We are calling this equation number 1. So RSS was a very simple matter, the difference between the observed and estimated, while I am presenting it in terms of the random error term. It looks like this. It looks like equation number 1. It looks like equation number 1. So from yi, when we are presenting the terms in terms of the random error, it looks like this. Why we are bringing ui? Because in a classical linear regression model, all the assumptions center around ui. So when we will consider the expectation, etc., the relevant variable will be ui. Therefore, we converted the entire thing in terms of ui. Any question? Up to equation number 1.
ম্যাম বলছিলাম যে থার্ড লাইনে ইউ এই মাইনাস ইউ বারটা করতে আসছে এই যে
This one.
হ্যাঁ হ্যাঁ
You know, what is the value of y bar?
আলফা প্লাস বিটা এক্স বার
Why? U bar will be not there.
আমার তো
I'm not talking about the estimated part. I'm talking about the original part. Okay. So yi is equal to,
নর্মাল ইকুয়েশন থেকে যেটা আসছে ওটা নয়
where you are getting normal equation here. Yi is equal to alpha plus beta xi plus ui. Then summation yi normal equation is in terms of the residual, not in terms of the error.
ওই ওয়াই বারটা ইজিক্যাল টু আলফা প্লাস বিটা এক্স বার প্লাস ইউ বার
Look at this. Okay. Okay, Darpak.
হ্যাঁ ম্যাম
So U bar is very much there in Y bar. Any other question? So I'm proceeding. So one by one, I'll consider each of the 3 terms. There are 3 terms here when I'm converting the equation in terms of, or converting RSS in terms of UIs. We have 3 terms. So one by one, I'll consider the 3 terms. So I'm starting with the first term, summation ui minus u bar whole square. Summation ui minus u bar whole square. So let's first consider the first term, expectation of summation ui minus u bar whole square. Okay. So expectation of summation ui square minus n u bar square. If I write ui minus u bar, summation of ui minus u bar whole square, this is equivalent to summation ui square minus n u bar square. Summation ui square as it is, u bar I am writing as summation ui by n. So u bar square is summation ui whole square divided by n square. Next, summation ui square I am keeping as it is. N by n square is 1 upon n. And if I consider summation ui whole square, actually I get summation ui square plus, you can write double summation ui uj. Double summation ui uj. I and j are running from 1 to 2n and I not equal to j. Double summation ui uj. Next, I'm operating expectation on each of the 2 terms. Summation expectation of ui square. Expectation of ui square is sigma u square. So summation expectation of ui square means n sigma u square. Minus 1 by n summation expectation of ui square. That means again n sigma u square. So minus n sigma u square by n, which is simply sigma u square. Expectation of ui uj, that is equal to 0. So minus 1 by n, double summation expectation of ui by uj is nothing but equal to 0. So finally, expectation of ui minus u bar whole square reduces to n minus 1 sigma u square. N minus 1 sigma u square. We are calling this equation number 2. Equation number 2. Any question? Look at the steps carefully. So I'm moving to the second term. Second term is beta hat minus beta whole square into summation xi minus x bar whole square. And I have to take expectation of that. Expectation of beta hat minus beta whole square into summation xi minus x bar whole square. So, if I operate expectation, it is summation xi minus x bar whole square into expectation of beta hat minus beta whole square. Now, expectation of beta hat minus beta whole square, is it variance of beta hat? Is it variance of beta hat? Everybody?
Yes.
Yash? Is it variance of beta hat?
Yes, ma'am.
Okay. How it is variance of beta hat? Would you please tell me the
The
variance of beta hat?
beta hat minus x beta hat minus expectation of beta hat তার whole square ম্যাম, তো ওটা তো variance of beta hat.
Okay. And then in case of expectation of beta hat, can we put beta?
Beta, yes ma'am, beta put করতে হবে.
Okay. Very good. So it is variance of beta hat. Summation xi minus x bar whole square into variance of beta hat. Now variance of beta hat is sigma u square divided by summation xi minus x bar whole square. We derived this. So summation minus x bar whole square will cancel and it reduces to simply sigma u square. We are calling this equation number 3. Any question? Any problem?
I mean summation xi minus x bar ওটা constant
Which one?
একদম সামনে মানে এক্সপেকটেশন নেওয়ার পর
This one?
না না না
Summation
তার
xi minus x bar whole square.
হ্যাঁ মানে এক্সপেকটেশনটা বিটার উপর ওই জন্য বলি
Xi we are considering non-stochastic.
আচ্ছা
So you know you have data on xi and you have knowledge on x bar. So for each of the observation you will get the value. Okay.
yes
So it is not stochastic at all. Xi we are not considering stochastic here. We are considering the sufficient condition. So we are considering xi is non-stochastic. So we are presenting the thing in this way.
okay
Got it?
yes ma'am.
So the second term gives the value sigma u square. Finally, we are coming to the third value. Beta hat minus beta into summation ui minus u bar into xi minus x bar. The 2ab part. this part. Okay. So I consider the third part, 2AB part. So it is expectation of beta hat minus beta summation ui into xi minus x bar. So I'm multiplying this ui with xi minus x bar. And there is one more term, minus beta hat minus beta u bar, minus sign is there. So minus beta hat minus beta u bar summation xi minus x bar. So I'm splitting it into two parts. Everyone? Why I'm splitting it into two parts? Because if I can split it into two parts, since u bar is a constant, I can write it as summation xi minus x bar, and that is equal to 0. This is nx bar minus nx bar. So it is always equal to 0. So it is expectation of beta hat minus beta into summation ui into xi minus x bar. Okay. So look, beta hat minus beta. So beta.
একবার আগের স্লাইডটা একটুখানি হোল্ড করবেন?
Yes.
হয়ে গেছে।
Previously, we found that beta hat minus beta is wi ui. Beta hat where beta hat minus beta, you know, is wi ui, where wi is xi minus x bar divided by summation xi minus x bar whole square. Okay. So here I am presenting beta hat minus beta as summation xi minus, actually it was beta hat minus beta, you know. So that I am presenting as, instead of writing, you know, sorry, yeah, I forgot to add summation sign. So instead of writing beta hat minus beta, I am writing summation xi minus x bar into ui divided by summation xi minus x bar whole square. The other part is already there, summation ui into xi minus x bar. Okay. I'm keeping, now I'm operating expectation. So 1 upon summation xi minus x bar whole square, the non-stochastic part I am keeping outside the range of expectation. So I have to take expectation of ui into summation xi minus x bar whole square. Okay, the two terms are same, so it is whole square. I'm getting summation xi minus x bar into ui. Here also I'm getting another summation xi minus x bar into ui. So similar terms. So this is summation ui into xi minus x bar whole square. Okay. Next, this is equivalent to summation xi minus x bar whole square expectation of ui square. Actually, I'm considering the whole square as well as the expectation. You can do it using two steps, no problem. So summation xi minus x bar whole square, expectation of ui square. And here, double summation xi minus x bar into xj minus x bar, expectation ui uj. Double summation xi minus x bar into xj minus x bar, expectation I am operating on ui uj component, expectation ui uj. So first what you can do, you can write expectation, keep it outside the third bracket, and you can write summation xi minus x bar whole square into ui square, and double summation xi minus x bar into xj minus x bar ui uj. And in the next step, you can operate expectation on ui square and ui uj. Okay. So if you like, you can follow two steps. First you consider the spread of the whole square, and after that, you can operate expectation. Whatever be the thing, this expectation of ui uj is equal to 0 by the assumption of non-autocorrelation, and this expectation of ui square is equal to sigma square. So this reduces to sigma square into summation xi minus x bar whole square divided by summation xi minus x bar whole square, which is simply sigma u square. So the third term simply provides us sigma u square. This is equation number 4. So once I get equation 2, 3, and 4, I'll plug these in equation number 1. I'll plug this in equation number 1. Okay. So if we plug the values in equation number 1, expectation of RSS is equal to n minus 1 sigma u square. If you look at equation number 1, it is n minus 1 sigma u square. Equation number 2, it is n minus 1 sigma u square. Then simply sigma u square. So the second term is simply sigma u square. The third term is also sigma u square. And in equation number 1, we have minus 2 this entire thing. So it will be minus 2 sigma u square. Once we adjust the matter, we get this is equal to n minus 2 into sigma u square. Okay. So what we are getting, we will start with expectation of EI. In the due course, what we are finding that RSS by N, that is expectation of EI, is not the unbiased estimator, rather unbiased estimator for sigma u square, rather RSS by N minus 2. That is the unbiased estimator of the sigma u square. So we started with expectation of EI, which is RSS by N. However, we find RSS by N is not the unbiased estimator for sigma u square. Rather, RSS by N minus 2, that is the unbiased estimator for the sigma u square. Hence, SU square. For the sample counterpart for sigma u square, generally we use SU square notation. So SU square is equal to RSS by N minus 2 is an unbiased estimator of sigma u square. RSS by degrees of freedom in a two-variable regression model, the degrees of freedom is N minus 2. N is the number of observation and two parameters we need to estimate, alpha and beta. So the degrees of freedom is given by N minus 2. If there are k number of parameters, the degrees of freedom in general will be N minus k. So for a simple regression model, the degrees of freedom is N minus 2. So RSS by degrees of freedom, that reduces to the unbiased estimator of sigma u square. And this form is invariant to increase in the number of regressors. So what I am telling, this RSS by degrees of freedom, this formula will remain unchanged if I increase the number of explanatory variables. So first, here I am considering the regression model. This kind of model. Now I can extend it as this is K. So in that case also, SU square will be RSS by degrees of freedom. Only the degrees of freedom will change. It will be n minus K. Here it is n minus 2. Now, if I consider a K variable regression model, if the number of explanatory variables are K, in that case, the number of parameters you need to estimate, that is, this beta 1, beta 2 up to beta K and this beta naught. Okay. So K number of parameters you need to estimate, and for that matter, we get the degrees of freedom to be n minus K. So the standard formula or the basic formula of SU square RSS by degrees of freedom, that remains unchanged if you increase the number of regressors. Okay. So the main thing is SU square is equal to RSS by degrees of freedom. That is the unbiased estimator of sigma u square. Now, if it is this one, then in the variance of beta hat formula, we had the formula sigma u square divided by summation xi minus x bar whole square. So this sigma u square will be replaced by SU square. If we do not have any knowledge about sigma u square, we have to replace this sigma u square by SU square. So basically, in a two variable case, variance of beta hat reduces to so this we call the estimated value of V of beta hat, estimated value of variance of beta hat. Next, in case of variance of alpha hat, we need to replace this sigma u square by SU square. So the formula becomes sorry, I don't know how to so this is okay. So this is all about how to estimate or how to find out an unbiased estimator of sigma u square. Any question?
ম্যাম ওই ভ্যারিয়েন্স অফ বিটা হ্যাটের স্লাইডটা দেখান।
Variance of beta hat?
ওই যে আগে একটা ওই বিটা হ্যাট বেস্ট প্রপার্টির ওই একটা আগে স্লাইডটা যাবেন ওই যে
This one?
হ্যাঁ 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 হ্যাঁ।
Yes, what's the question?
ম্যাম লিখছি।
I simply replace sigma u square by its estimated value, SU square, which is RSS by n minus 2. Similar thing I did in case of variance of alpha hat. Sigma u square I replaced by RSS by n minus 2 or SU square. Okay. Any other thing? Any other question? So with this, we complete the analysis on estimation part. Okay. The estimation part is complete. Next, we will move towards hypothesis testing. However, before moving towards hypothesis testing, we have to talk about ANOVA part, analysis of variance part. Okay? Once we understand the ANOVA part, once we understand the idea of goodness of fit, then only it will be appropriate to plan for hypothesis testing. So I'm moving.
Ma'am,
Yeah,
move to the slide right.
I didn't get you.
Ma'am, can you hear me?
Yes,
Yeah, ma'am, could you move to the this one, the one you're at right now?
this one,
No, ma'am, the one right before this one.
this one.
Yeah. Okay, I missed out on that last line. Right. Okay, ma'am, thank you. Thank you.
Analysis of variance part. Okay, so in regression analysis, we are familiar with three terms: TSS, ESS, RSS. Already we have did several things based on RSS, residual sum of squares. There are two things as well. In the left hand side, actually we are trying to capture the variation in yi. Now, if I try to capture the variation in yi, I need to consider summation yi minus y bar whole square. How observations are moving around the mean value. Okay? And since we are not interested about the direction, we should consider the square. And since we will consider all observations at a time, we will consider summation yi minus y bar whole square. Okay? So, in a regression analysis, we want to capture the variation in yi around its mean. This is called the total sum of squares. Total sum of squares. Okay, the variation in yi is called the total sum of squares. This total sum of squares can be decomposed into two parts: the explained part and the residual part. The explained part, which will come from the explanatory variables, and the residual part or unexplained part, which will come from the residual component. Okay? Or the error component. Error is not observable, therefore we consider the residual component. So variation in yi is basically, in a regression framework, equal to ESS plus TSS. Sorry, ESS plus RSS. Okay, the ESS is beta hat square this can be also presented as okay. Are you understanding the equivalence between beta hat square summation xi minus x bar square and this term? The formula for beta hat okay, so beta hat into summation xi minus x bar whole square is nothing but summation xi minus x bar into yi minus y bar. So in this formula, if you replace one beta hat multiplied with summation xi minus x bar whole square by summation xi minus x bar into yi minus y bar, it reduces to beta hat into summation xi minus x bar into yi minus y bar. Okay. So ESS is given by this part. It comes from the explanatory variables. It can be either presented by beta hat square summation xi minus x bar whole square, or it can be presented as beta hat into summation xi minus x bar into y minus y bar, similar things. Okay. And the other component is the unexplained part, the residual part, which we are calling the residual sum of squares. Okay, residual sum of squares. So this one, summation ei square, is the residual sum of squares. Okay, so we can reach at this equation if I start from summation ei square. So let's start from summation ei square, the RSS part. This is equivalent to summation yi minus yi hat whole square. And already we checked this is equivalent to summation yi minus y bar minus within bracket yi hat minus y hat bar, or the way I have written, minus yi hat plus y hat bar, because y hat bar and y bar are equivalent. Okay. This can also be written as this capital yi minus y bar can be replaced by small yi minus beta hat capital xi minus x bar appears from this yi hat minus y hat bar component. So it is beta hat into capital xi minus x bar as we got earlier. So it is also beta hat into small xi. Capital xi minus x bar is nothing but small xi. So we can write this in this format too. So if I write the thing in this format, summation ei square is equal to, if I consider the whole square, summation of yi square plus beta hat square xi square minus 2 beta hat xi yi. And if I operate sum on all of the three terms, it is summation ei square is equal to summation yi square plus beta hat square summation xi square minus 2 beta hat summation xi yi. Okay. Now summation xi yi, that is summation xi minus x bar into yi minus y bar, is equivalent to beta hat into summation xi minus x bar whole square from the beta hat formula, as we did. Beta hat into summation xi minus x bar whole square is equivalent to summation xi minus x bar into yi minus y bar. So this I can replace by this summation xi yi, I can replace by beta hat into summation xi square. So if you adjust, you are getting summation yi square minus beta hat square summation xi square. Summation ei square is equal to summation yi square minus beta hat square summation xi square. If you readjust the equation, you are getting summation yi square. This, if it comes to this point, it will be plus. So summation yi square is equal to beta hat square summation xi square plus summation ei square. Or in other words, TSS is equal to ESS plus RSS. So this is a very important relation in context of analysis of variance. TSS is total variation is exactly equal to explained variation in yi plus unexplained variation or the residual component. So it shows that total variation in the observed y values would about their mean can be partitioned into two parts. One attribute to the regression, that is the explanatory part, and the other to random forces, because not all actual y observations lie on the final line. Okay, so all the variation we will be not explained considering the set of explanatory variables. There will be some unexplained part. All the observations does not lie on the fit. Any question?
Ma'am, could
Everything.
you explain this? Uh, Sorry. Ma'am, could you explain the like the segment written below the equation TSS ESS that equation? Could you explain that written segment?
This one.
No, ma'am. The text right below that.
This one. The
Yes,
text.
ma'am.
I'm telling that total variation in yi. So total variation in the observed y is yi values about their mean. What I am considering in the left hand side, summation yi minus y bar whole square. This one. Summation capital yi minus y bar whole square. This I am considering, which we can summarize by small yi. So it is the total variation in observed y values about their mean. And this can be partitioned into two parts. One, attribute to the regression. Attribute to the regression means the explained part, the explanatory part, explanatory capacity of the model. And the other to random forces. This part, the unexplained part, the unexplained variation that comes from the random forces. So, and the other to random forces, because not all actual y observations lie on the final line. You will have the fit around the scatter. So all the scatter point will not lie on the fit. So there is some error. There is some unexplained part. Okay, that I want to indicate. Adatri, got it?
Yes, ma'am.
Anyone, anything else? So since in the ANOVA context, we are finding that when I'm considering the total variation in yi, there is explained part, there is unexplained part. I have to consider the idea of goodness of fit. How much, or how large the explained part can be. Okay, larger the ESS component and smaller the RSS component, better will be the fit. If I can improve this ESS and reduce this RSS, I am moving towards, the best fit. If RSS is equal to 0, the entire variation in yi can be explained by variation in xi. So that is the best fit. All the points will lie on the line. Okay. However, there will be some residual component, as you know. So on the basis of this idea, we can develop a natural idea of goodness of fit. The natural idea which emerges from this equation is ESS by TSS. As ESS by TSS moves towards 1, this is a best fit. The total variation can be explained by the set of explanatory variables I have selected. Okay. So ESS by TSS, the proportion of the explained component with respect to the total variation can be considered as a measure of goodness of fit. This can be considered as a measure of Are you agreeing with this? ESS by TSS can be considered as a measure of goodness of fit.
Yes, ma'am.
Rest of the students, what do you think? Can we consider ESS by TSS as a measure of goodness of fit?
হ্যাঁ মানে ওই ওয়াই আর ওয়াই হ্যাটের যে ডিফারেন্সটা সেইটা ওই প্রত্যেকটা মডেলটা ওইটা এক্সপ্লেন করতে পারবে নিচেতে
Yes,
যেটা আছে।
if it moves towards 1, if I consider ESS by TSS as a measure of goodness of fit, when it is moving towards 1, the entire variation in yi will be explained by variation in xi. In the left hand side, I have summation yi minus y bar whole square. In the right hand side, I have summation xi minus x bar whole square. Okay. So if ESS is very, very close to that of TSS, total variation, it means that variation in xi along with the regression coefficient beta hat can explain almost the entire variation in yi, isn't it?
হ্যাঁ ম্যাম।
Okay. Rest of the students, O3, what do you think? Can we consider ESS by TSS as a measure of goodness of fit? O3 has left the meeting. Rest of the students, what do you think? Are you sleeping? Or you are very tired? Shambhav? What is your idea about this measure of goodness of fit? Is it the right measure? Tell me, what do you think? Okay, Shambhav, your voice is not audible. You are not audible. On the basis of analysis of variance, ESS by TSS emerges as a measure of goodness of fit. Okay, so this we define by R square, capital R square. Actually, in a two variable analysis, it doesn't matter whether you consider the simple R square or partial R square or multiple R square. However, if we consider more than one explanatory variables, all R square will indicate different meanings. All R square will indicate different meanings, So generally, we present the measure of goodness of fit using the multiple R square. Okay. So ESS by TSS is the natural measure of goodness of fit, which is beta hat square summation xi square divided by summation yi square. Okay. And as we keep on adding the number of explanatory variables, the ESS increases, the explanatory power of the model increases, and hence R square will also increase. TSS remaining constant. TSS remaining constant as you go on increasing the number of explanatory variables, your explanatory capacity will improve and ESS by TSS will also improve. Okay, so R square, which is ESS by TSS, is considered as a measure of goodness of fit. And remember that as you increase the number of explanatory variables in your model, ESS increases, TSS remaining constant, and hence R square increases or improves. Later, when I'll give an introduction to K-variable model, I'll discuss the matter whether really we can go on and on increasing the number of explanatory variables or not. If R square, which is ESS by TSS, appears as the measure of goodness of fit, in that case, it seems to be actually we have to go on increasing the number of explanatory variables to improve the goodness of fit. However, in reality, is it possible? You will find that as you increase the number of explanatory variables, number of parameters to be estimated, that will also increase. And that in turn will reduce your degrees of freedom given by n minus k. And as degrees of freedom falls, the acceptability of the regression model, that will be questioned. So all these issues are there. However, in a two variable case, we are considering typically a single explanatory variable, so all these issues are not appearing at all. So to begin with, we can accept R square, which is equal to ESS by TSS, as a measure of goodness of fit. So more excess helps to explain the model better. Okay. However, there is a corresponding loss in the degrees of freedom as n minus k goes down. So this point I'll also elaborate later, because at this point it is not relevant to discuss because I have a single x only. So there is no question of having 2 or 3 or 5 explanatory variables in our construct. Okay. So I hope you understood the idea of TSS is equal to ESS plus RSS. And if this is the analysis of variance equation, in that case, the natural measure of goodness of fit will be ESS by TSS. And if ESS by TSS is the natural measure of goodness of fit, that indicates as we increase the number of explanatory variable in the model, the explanatory power of the model improves, and that improves the goodness of fit. Any question?
Ma'am,
Yes. Yes.
Is number of explanatory variables. Um, like ESS increases and it eventually moves TSS, right?
TSS will not increase. TSS is variation in
ESS,
EAS. As ESS increases, what you are
not
saying?
TSS. Ma'am, as we increase the number of explanatory variables,
Yeah.
ESS
ESS improves.
increases and eventually it converges to, yeah,
Eventually,
and
the goodness of
eventually it
this
moves to
improves.
TSS.
Yeah. Eventually, ESS by TSS moves towards 1. However, ESS cannot be greater than TSS. Okay? TSS we are splitting
Okay,
into
ma'am.
two parts. ESS and RSS. So as ESS improves, the RSS moves towards 0. However, ESS cannot be greater than that of TSS. Okay? So what will
Ma'am,
be the
ESS,
range of R
Okay, ma'am.
square? Anyone, please tell me, what will be the range of this R square? What is the
Ma'am, 0 and 1.
value? The minimum possible value is? Yeah, somebody tried to tell. What is the minimum value?
মিনিমাম 0 হবে।
0 হবে. So what does 0 means here?
TSS equals to
ম্যাম
RSS.
এক্সপ্লেন্ড সাম অফ মানে টিএসএস দিয়ে এক্সপ্লেন সাম অফ দিতে হবে।
The variable we are considering in yi, that is not working at all. Xi cannot explain yi. That is the meaning. If xi cannot explain yi, okay, any part of the variation in yi cannot be explained by xi, in that case, ESS will be absolutely equal to 0. The entire variation will be captured by the residual part, unexplained part. Xi is not the right variable to explain yi. So the minimum possible value is 0, while the maximum possible value is 1. So in that case, there is no residual. All the scatters are lying on the feet. That is the context. So the range of these R square is from 0 to 1. It lies between 0 and 1.
ম্যাম
Do
বলছিলাম যে
anyone have any question?
হ্যাঁ ম্যাম এই এক্সারসাইজটা যখন বাড়তে থাকে তখন ইএসএসটা কেন বাড়ে ওটা বলবেন?
হ্যাঁ, কি বলছো?
এই যে ম্যাম ওই
First,
নাম্বার অফ এক্সপেন্টরি
considering
ভ্যারিয়েবল।
suppose you are considering the demand equation, you are considering demand is a function of price only. However, in reality, demand is not only explained by price, it is also explained by income. It is also explained by taste and preference. It is also explained by geographical location. It is also explained by gender. It is also explained by parental education. Okay, so there are too many things which explains demand. However, if you consider only the price, in that case, is it possible to capture the variation in demand using price only? What do you think, Darpak?
না
Okay, because if you consider the price, the effect of income, effect of prices of related commodities, effect of taste and preference, gender, education, everything will be there in the residual component, because you are not explicitly bringing all these things in your analysis. So it will be there in the unexplained part. However, one by one, if you bring income, prices of the related commodities, taste preference, gender, all these things, in that case, you will be able to explain the demand in a better way. So this is the idea. So as we increase the number of explanatory variable, there will be an improvement in explanatory power of the model. Okay? So R square will improve. Okay, so I'll stop here because I'll not start the distributional aspects. In the next class, I'll start the distributional aspects and I'll move towards hypothesis testing. So please check these parts, the estimation of sigma u square, then the analysis of variance, and from there, how we develop the idea of goodness of fit, how we develop the measure of goodness of fit.
Ma'am,
Yes.
please mark me present. Actually, my microphone was not functioning well, so I couldn't respond.
Okay, I'll do so.
I'm number 39.